when it comes to questions for this talk, we're going to try something new for our worldwide audience. If you want to ask a question, stick a hand up. I will sort of point at you, and Marius in the red will run up to you with a microphone, and then the world will know what you want to say. So at the end. Okay, so that's it. So over to Mark.
Okay, that's good. That's out of the way. All right, the future of networking. By networking, I do not mean free beer and pizza, chatting to the same folk you do every month because the thought of chatting to somebody else kind of fills you with a crippling anxiety. Because we're all experts in that already. I'm talking about computer networks, which these guys know a lot about. And I'm guessing most of you have used a computer network at some point, but you're not necessarily too familiar with the guts of how the devices that make them up are architected. I've grandiosely titled this the future of networking. The reality is that networking is such a large industry that I can't really talk about everything that's going on in it. So I'm going to talk about 2 or 3 things that I know reasonably well or know more about. So I'm not going to talk about the Internet of Things. I'm not going to talk about wireless, Wi-Fi. I am not going to talk about security stuff. I'm not really going to talk about protocols, and that includes IPv6, much to Rachel's disappointment. Not because IPv6 isn't the way of the future, it definitely is. It's sort of been solved from a implementation point of view, and we're just waiting for the rest of the world to kind of catch up. What else? Networking also is afflicted by jargon in the way that most of the tech industry is, but possibly more so. And if you're not familiar with it, it's very easy to get lost. And there's a good chance I will use terms that I think are common that in fact you don't understand. So please feel free to ask questions as we go along and make Marius jump up and give you the microphone. In case anything isn't clear, or if you're just want more detail. I'm kind of trying to keep this at a relatively high level without going into too many details. But if you are interested in some of the details, I might be able to give you them, or at least sort of point you in the right direction. So feel free to ask questions as we go along. That's probably a good idea. Right. So, who am I? Why am I giving this talk? I'm Mark. I studied electronics and computer science at Edinburgh and graduated 10 years ago now. My networking-related achievement in that was I built a wireless router in my second year at a point where, this is before ISPs were shipping out wireless routers to people, which wasn't very good. It ran in ad hoc mode. I think I used it. I don't think my flatmates did. But I learned the perils of upgrading Debian before you really should, and other networking fundamental screw-ups through doing that. I was part of the TARDIS project, which is great. If you're still at Edinburgh University and you're not involved, you should get involved. They do good things. And yeah, so I did that and learned all about computers and stuff. Didn't actually take the computer networking course, but through the electronics side, I kind of learned a lot about communications in general. I spent a few years after that in the electronic design automation industry, which was great. And then I got the opportunity to work for Cisco Systems in 2010. At that point, so the team in Edinburgh was great. A lot of them had worked at DEC back when they were still a thing, before Compaq bought them because they wanted to get big. Some of them had worked for Spider, who are a local networking company in the early days. And there was a lot of experience and a lot to learn from them. They'd also worked on some of the really big projects within Cisco internally. They worked on a thing called Cisco Express Forwarding, which was the kind of backbone of what allowed Cisco routers to go fast just after the millennium. And they worked on IPv6 support, funnily enough, NetFlow and other things like that. So yeah, great team, great place to learn. But unfortunately, at the end of 2014, we were told that they were going to close the site. In fact, it was us and our sister site down in Reading were both getting shut. It was a shame, but to be honest, the writing might have been on the wall. The reality is that the traditional switching and routing market that we wrote the software for, the growth wasn't really growing, or it wasn't growing as fast as it was, and for Cisco, it was all about finding the next growth market. So it makes sense when you're a company that size to move people from one area to another, and the way they did that was by closing our sites and then buying a few startups in security or Internet of Things or whatever it is. So we were all a bit worried because there were a good 40 of us or so about to be dropped in the market with basically the same CV, which was a bit worrying. But it turned out that Brocade Communications were looking for engineers who knew how to write networking features to work for a part of their company. It was a company that used to be called Viata. There was a startup that they bought that had this software router product. And it was good, and they had just made it even better, but now they needed to get all the feature support so that they could actually land some big customers and make everybody realize how amazing it was. And that's what I've been doing for the last 2 years. Brocade have been really good to us. It's been a much more modern environment than Cisco. We get to use Git, and we get to we get to have, well, what else do we do? We get to use Git. Git is the main thing that I really like from it. And it's cutting edge technology for the networking industry. So it's been really interesting. But last year, Broadcom announced that they were going to acquire Brocade. They're not interested in the IP assets or part of the company that I work within. So I'm going to work for another company in the future. I literally cannot say anything other than that. Maybe in some future month at TechMeetUp, I'll say I work for a different company. But at the moment, that's all I can say about that. It's the one thing you cannot ask questions about. The reason I'm kind of going into so much detail is because it actually reflects the ongoing changes in the networking industry. Cisco had I joined Cisco really kind of peak Cisco or at least within the traditional networking area. And because that growth has softened, it was Brocade who were investing in these new technologies that were really, that were hiring, and we'll see where I end up. It's all looking kind of interesting to see where things are going. Everything is kind of definitely moving, and there's a lot of churn. And hopefully that will kind of come out in the rest of this talk. But first, I want to give a bit of context and a bit of history to kind of set the scene before I talk about the future of things. Right, does anybody know who these people are?
They were the founders of Cisco.
Yes, do you know what they're called?
Mr. and Mrs. Cisco.
Almost, they were married. So this is Sandy Lerner and Len Bozak. They both ran networks at Stanford University. Len ran the computer science department and Sandy ran the business department. And the networks there had different protocols. And the romantic story is that they really wanted to sext each other at work, so they built the first multi-protocol router to let them do that. The reality is probably a bit murkier than that. I think, allowing these networks to talk to each other was a sort of a bigger picture thing than just the two of them. And there were various people that wrote parts of the software and built the hardware to allow it to happen. But these are the two people that founded Cisco, started the company, borrowed the IP assets in order to do that, then spent a couple of years squabbling with Stanford about exactly what was going to happen there. The end result being that there was a settlement Stanford got to license Cisco's products, and it all ended reasonably amicably until they got squeezed off the board when Cisco started getting really big, and eventually they got divorced. But they did get 170 million out of it, so could be worse. So yeah, that's how Cisco came about. So like I said, the first product they had was this multi-protocol router. Routers had existed before then. Sometimes routers, they were also called gateways, and the idea was that these were devices that would sit on the edge of your network and then would speak to the connect to a telephone line or whatever, and connect to the rest of the internet at a high level. What Cisco were very well placed for is that IP networking was just about to kick off. And they very quickly specialized in IP networking. Although I think to this day you can still get the sort of multi-protocol support on the routers as well if you really need it. If you've got legacy networks you need to connect. Right, what's a router? Does everybody know what a router is? Does everybody think they know what a router is? Okay. So just in case anyone's not sure, a router is a device that allows computers on different networks to speak to each other. There we go. Okay, so you're on computer A, and your computer wants to speak to computer B. But you're in different networks. Let's say the one on the left is the business department at Stanford, and one on the right is the CS department. And there might be other networks as well. The router knows how to take packets from one network and say, okay, I'm connected to this network over here as well, and I know this machine, this address is within that subnet, so I'll send the packet over there. Easy, right? Where the story gets more complicated is that there might be further networks beyond the 10.3.1 that 10.1 might also want to connect to, right? For example, this is 10, anything starting with 10 is a private network. If you want to connect to the more general internet and the servers off there, there will be some sort of device that connects off the internet, and this router needs to know at least one route to get your packets off to there. And often the reality is there's many routes that it needs to know about in order to make the whole network work effectively. But at a very simple level, this is what's going on. Okay, so it's all about forwarding packets between networks. Right, where was he? There's another kind of networking device called a switch. And sometimes these things get conflated, but they are classically separate devices. Oh, okay. So I've written the letters L3 and L2 next to these things. These are protocol layers in the TCP/IP stack. There's not the OSI stack that you might have learned about at university, because nobody uses it. L3 is IP networking. TCP is L4, and then the applications really are L4 above that. L2 is Ethernet and sort of physical networking. L1, I guess, is the actual hard media, like the wires and cables, I think. L2 is how we actually get the raw bits and bytes across a piece of cable to something else or something else. So the problem, the reason that switches came about, if I go to the next slide, is because this is kind of what an Ethernet network's like. The model is basically the tin can network. So the very simplest, you've got these two cans at either side, and you can shout down one end, and somebody at the other end has to sit with their ear next to it, and the string vibrates, and the sound passes along it, and then they can hear the sound. But the problem is, if you both try to speak at the same time, you can't hear anything, because the line gets distorted and it all goes horribly wrong. So with a tin can network, you can only speak one at a time. And Ethernet's the same. Over a single bus, you can only ever have one host actually communicating across it at once. And this gets even more complicated when you start adding more cans or more computers onto your network, because you add NOTs in the middle of this, or you have some kind of junction box, a hub or something in the middle to allow this network to get ever bigger. But now there's even more chatter, and how do you figure out who's going to speak at one time? Initially, this wasn't so much of a problem because computers were so fast that they would be able to kind of find a space. But eventually, enough computers were all connected to the same network that they were spending half their time shouting over the top of each other and not getting anything done. Switches was the technology that saved us from that. So at the top, I've kind of what I've just described. A hub is basically a big wrapper around a piece of wire, effectively. Any packet that comes in gets broadcasted to all the other packets, because effectively it's one big bus that they're all connected to. The difference with a switch is that a switch can learn which host is connected to which port on it outside of it. So it means that if you are on A and you're trying to speak to G, the first time it will send the packet everywhere because it doesn't necessarily know where G is yet. And then it gets a response from G, and G says, I'm here, I'll have that. And the switch goes, aha, you're G. I know where you are now. And every other packet from A that is destined for G will only go to G. And even better, if D wants to speak to G, well, it doesn't have to broadcast that packet now, it knows where G is. So what switching does is it basically means that each of those little black lines is one tin can network from end to end. And it means it's like you've got a treehouse in the middle of your tin can network where you've got somebody very busily listening to each of the tin cans and going, okay, I hear what you're saying, and then hobbling over to the next one and then shouting that along, except doing that very fast. So that's switching. So these are the two key technologies that have mostly made up the internet, or certainly it made Cisco a lot of money and most networking companies a lot of money. Right. So at this point, the hardware and software was, by our modern standards, fairly rudimentary. Obviously, they were cutting edge, but you basically had a box with a bunch of network connectors in it, and then you had a processor that was running some kind of effectively real-time operating system. I think there may have been some networking vendors that might have had time-sharing operating systems on it, but for the most part, they are these run-to-completion, very simple operating systems that can really only do one thing at a time. Like I said, they were based on the CPU. They kind of hogged the whole attention of the CPU. And then every time a packet comes in, there'd be an interrupt signal, and it would go, okay, I've had a packet. Let's stop everything else we're doing. Let's go off and figure out, okay, where's this packet going? Which interface does it need to go out? And then it would send it away there. And then it would go back to whatever else it was doing. It was usually sitting waiting for config or something like that, something not very exciting. Each vendor, so in this early days, you've got Cisco, you have 3Com kind of appear. Eventually, you've got the likes of Juniper. There's, other vendors are kind of starting to kind of pop up. But each vendor has their particular hardware and how they like to operate, and they have their software that runs on their box. Right? So there's very tight integration between the hardware and software because you want to kind of optimize as best as possible for what you know you're actually shipping on. And in the early days, there's naturally a limited feature set of what people are really expecting us to do. I mean, they were already amazed that we could get more than 2 computers to be on the same network. But that did eventually start to change. Right, does that all make sense so far? Okay. Right, so that's the kind of the early basics. The thing about networking is it's really all about scale in various ways. Customers always want more ports to plug things into. They want faster ports, different rates, from megabit to 10 megabit to 100 megabit to gigabit to 10 gigabit to 40 gigabit to, well, apparently now 25 and 50 gigabit are where things are at. they wanted more features. So initially, like I said, they were just happy that it worked. But then we're like, maybe we need to secure this a bit. Maybe we need firewalls. Maybe we need things like access control lists, which are a way of kind of saying, well, these IP addresses are fine, but these ones not so much. Maybe we want to monitor this traffic and do things with that. All kinds of stuff, all kinds of amazing things that I'm not going to talk about. Became popular. On the routing side of things, you've got different protocols. So BGP is one of the big ones, and you also have OSPF. You have lots of other more niche kind of things. You've got the various other protocols and features. Anyway, so all this stuff is kind of getting demanded. Now, as you get more ports and as speeds get faster, you hit the limits of what you can actually do on a single CPU. So the example here we've got is, let's say you've got a 24-port switch. They're all 10 gigabit interfaces. That is 20 million 1500 byte packets every second. I say 1500 bytes because that's the maximum size that Ethernet frame can be. You could actually have more packets than this because not every packet that comes in is maximum size. They could be quite small. So this is sort of the lower bound. That means that on a 2 gigahertz processor, which is quite a fast and fairly comparatively modern one for what I'm talking about, you have only 100 instructions to figure out what packet is this, where did it come from, who wants to, where is it going, are there any features that need to be applied to this? Do we need to, all these kind of checks. Getting all that done, getting it read in, getting it all analyzed and then sent is a pretty tough order for 100 instructions on a microprocessor. So that wasn't great. So as an industry, we had to figure out how are we going to get around this, or what are we going to do to optimize around this. And first, what they did is, like I said, they had these interrupt-based approaches. So they figured out, well, if we can get this the control side of things, they're just sitting waiting for config. If we can get that to pre-compute a bunch of stuff, like where these packets should be going, and just make it a big table in memory, then all that needs to happen in that interrupt is it just goes in and it looks up in the table and goes, okay, well now you'll go with that and out that interface. So let's do that. And that got them somewhere. And what that eventually evolved into is the idea of, well, actually, now you've got effectively this split between the control side of things and the data side of things. Why do we need to run them on the same processor? Why don't we have, in fact, 2 computers or even more, or two devices? And you start to see the beginning of these chassis devices that have a single controller that you go in and you configure. And all its job is to do is to sit and wait for configuration and also to do all the kind of dynamic computation that some of the routing protocols and the like need. And then dealing with when the config changes, updating all the line cards. And the line cards is where the packets are actually coming in and they're going out somewhere else. And all that is going to be configured on that is the bare minimum that it needs to know, which is if the packet is going to get routed locally, then it needs to know details of which interface there. Otherwise, it just needs to know I need to shove it to an interconnect that's going to send it to another line card, and it can worry about the details when it gets there. So that was in one phase of things. Even that, I mean, if you think about it, that problem with 100 instructions, you've still got that problem on the line cards, even though you've now freed up the processor to be able to kind of do the config stuff while the data stuff's happening. So hardware data planes was the next big innovation. So these are usually implemented as custom ASICs, which stands for Application Specific Integrated Circuit, off the top of my head. These are integrated circuits that are comparable in scale to a general purpose CPU, but they're optimized for a specific application. In this case, forwarding network packets. And they're usually built with a thing called a TCAM, which is a ternary content addressable memory, which is a kind of like a hardware lookup table that can actually have where each bit can have 3 positions, either on, off, or don't care. And that allows you to do what they call prefix matching. So when I showed you these networks, you will recognize those as IP addresses. You might recognize the slash and the number after it, and that was a network prefix, and that says that basically everything on this network is always going to have the first two places as 10.3, but any host could have a number, a more specific number in the last half. And that's the don't care aspect of it with TCAMs, right? You can apply this prefix, and that makes routing tables much easier to look up and much easier to work with. So we have these very complicated and very expensive to build and design and manufacture ASICs that can easily beat our limit, because you no longer have to worry about, or you worry less about the whole, on a general purpose CPU, of loading into memory, looking things up in the right place, getting, you don't have to bother with that because it's all kind of laid out for you. The trade-off is that they're very slow to program comparatively, right? You need to figure out that the control languages for them are usually quite complicated because they are custom designed, but the flip side is they're very fast. Once a packet comes in, they get routed almost immediately. So we kind of hit this point where you're cutting edge, like your really fancy stuff. You've got a big chassis, you've got a dedicated controller with maybe quite a beefy CPU if you're really lucky, and your line cards have these hardware data planes in them that can punt packets as fast as they come in at 10 gig plus kind of speeds. Right, so we're now in we're at a point where we have these networking devices. They're fast. They also support lots of different features, as I was saying. And to a certain extent, they start to sort of bleed into each other. You start getting routers that can actually act as switches to some extent, or they start having switch features within them. You get switches that start to learn more about what's happening at L3. They can actually do IP matches and the like, and or even worse than that, they are checking for things of a given application type and doing filtering of that. The layers all started to kind of get merged and mixed up. I've got a picture here of one of these things. This is the Nexus 7K. To give you an idea, that is the size of a relatively, quite a big standalone freezer. All right, so kind of it'd be about the size of this lectern. They're very loud because they get very, very hot. And they're also very, very expensive. So just one of those line cards, at least at some point, would have cost you £70,000. As you can see, there are, 8 of them in there, and then you've got the 2 controllers, which should be even more expensive, and then you've got the chassis and the power. Yeah, so Cisco's making an awful lot of money out of these things. And I'm sure they're relatively expensive to produce as well, especially when you consider the software costs. But apparently the Cisco CRS, which is the kind of core router stuff that they make, that some of those sell for like $500,000, possibly more. So at the top end of things, it gets very expensive. But even at you might have seen like the kind of classic one rack 24 port switches. Even they are easily tens of thousands when they come out. And this stuff is not cheap. There was one point in Cisco where I realized we'd had these Catalyst 4K devices sitting under the desk that needed to go into the lab. And they'd been there probably about 6 months because nobody could be bothered putting them in the lab. And I thought, you know what, I wonder how much this costs. And when I realized the value when they'd just been sitting as a footstool under my desk, I said, you know what, I'm going to go put this in the lab and start using it, because that's just a waste of money. Yeah. Ooh, where are we going here? Right, okay, so that is roughly where we are or where we were these days, to some extent. This is kind of what I was heading towards, which is to talk about where we're going next. And there's three big topics I want to talk about. One is disaggregation, we've got virtualization, and orchestration. These are all big fancy words. I will try and explain best what they mean when we get to them. The first one, disaggregation, literally means breaking things up. Aggregation is putting things together. Disaggregation is the opposite. What are we breaking up? Mainly, we are separating hardware and software. That's what we're doing. So the first big thing in this category that I can think of is OpenFlow, which came out of Stanford University. There was a professor there that I think he was possibly still bitter about how Cisco got its start. And he proposed this model where instead of having these hardware switches with quite complicated control features, control software, and lots of features in them, and being very, very costly, and having lots of these, and sometimes you'll cluster them, and really only one or two of them are actually using that extra complexity. He said, well, what about instead, we just got the dirt cheap, most basic ports that meet the speed that we need, make a very thin layer, which is just this hardware, and then a pretty dumb agent that sits on top of that. And then we have a really clever controller that runs as an application on a server somewhere. And it'll speak IPsec to each of these things, and basically it'll make decisions about how to configure these switches based on the information that's kind of coming to and from. And that was the model. And this, if you've heard the term software-defined networking, this is where it originated. Unfortunately, software-defined networking has sort of become a catch-all term for anything interesting that is happening in networking, which is why I've mostly not used it so far. So that's the switching side of things. The more interesting thing that's kind of happening now is what they call white box switching and routers. And the best way to think about this is a replication of what happened in the 90s with PCs. So we used to have mini computers that were made by DEC and the like. Nobody was going to need, what was it? There was a certain number of computers that we needed in the world tops. And then eventually there was a decision, well, actually, no, everybody needs one of these on their desktop. Everyone needs one of those in their house. Everybody needs one of these in their pocket. It rapidly changed at some point. And the big difference was that you went from, again, very highly integrated hardware and software that had to be bought from a vendor and needed specific support, to having fairly open standards where components could be sourced from different people. Integrators could put them all together into a single box, and you could run whatever software you wanted on it to some extent. And there's a much greater degree of flexibility and etc. And thus we have the PC revolution. This is only starting to happen in networking 20 years later. And the reason for it is that we finally have companies like Google, Facebook, and AWS that are just so huge and have these they have these massive data centers, and they were looking at the bill they were paying Cisco or HP or whoever, and they were like, this is crazy, guys. We're not even using half of this stuff. What's the point in this? And they realized, you know what? We can build our own, right? We're already doing it for our compute servers. They already had very optimized kind of hardware, and they had ways of dynamically provisioning these things in a pretty clever way. Why not do this for the networking equipment as well? So I think Facebook have possibly been the most active in terms of publishing what they've done. They've released details of their wedge and their backpack devices. They've got their own network operating system that they run on these things. They're trying to embrace open source and open standards as much as possible. And there are, I mean, these are some of the companies that are providing things at the different tiers. Broadcom are the world's biggest producer of network connectors. They're the big one. But there's interesting companies like Barefoot and I might be bear as in a bear rather than bear as in naked. I'm not sure. And Cavium, who are producing effectively ASICs that are programmable with an open standard that anyone can buy. That's fairly newish. You have, at the OS level, Cumulus are a company that do various things, but they're providing an operating system you could run on white box hardware now. Facebook obviously have their own. And I've kind of put apps here because I'm not really, I mean, this is the networking features that you traditionally think of, the routing stack. Free-range routing is actually just, well, if you've heard of Quagga or Zebos in the past, that's basically what that is. But I think like Cumulus and a few other companies had these massive patch sets where they took the open source version and sort of made it do something more useful, and they were just sick fed up of not being able to commit these, so they've created free-range routing as a project to sort of get that all merged into something else, which will no doubt end up being stale, and everybody else will have their own patch sets, but you know, that's how these things go. SnapRoot are an interesting company that are doing something different, where they have actually built from scratch networking stack and protocol stacks in Go, and they've got this sort of modular design where you can say, I want BGP, I want whatever. You just want BGP. Or I want BGP and OSPF because I'm crazy or whatever. We have these things all together in the same lump, rather than not having no choice around what you have. But it means you can have a really thin layer, and I think you can show them containers and do all kinds of fun, exciting things. AT&T recently announced that they'd built 2 white box switches. I think they worked with SnapRoot with Barefoot, maybe? I can't remember. A couple of folk to put together these switches. They ran them in their network for a while, and then they took them down, and were like, yes, we've done it. White box, here it is. As far as I'm aware, that is as far as they've got with it, or as far as they've announced. Like I said, your big web companies are doing more proprietary versions or internal things where they, unless they've released it as open source. It's not clear yet if this will be a feasible thing for smaller enterprises to actually do. It might be that the reason that networking hasn't disaggregated is because there just isn't the market for it. It isn't big enough. It can't afford. I mean, Google, Facebook can afford to get a team of network engineers to build this stuff from scratch. Most banks are not going to bother to do that, even if they are incredibly wealthy. They're not really interested in being technology companies to a certain extent. Some kind of think they are. Anyway, virtualization. Right, vRouters. I know about this because that's what I work on. I work on a virtual router for Brigade. This is basically just taking the software that ran on an actual physical router and turning it into VM in the same way that we've taken the software that runs on all computers and turned them into VMs and then shoved them in the cloud or whatever. The trick, yeah, there are various companies that do it. You've got, like I said, Brigade, we have an excellent one. Juniper's got one, even Cisco have got a virtual router of some sort. They were initially quite slow because you're kind of going back to those early days where everything is software, and you've got the problem again of you've only got so many CPU cycles. How do you actually deal with all the packets? Intel solved that problem for us. They gave us a thing called the Intel DPDK, the Data Plane Development Kit, where they got their brightest engineers to go down and figure out how can we cram as many packets through a CPU as possible. It can even do quality of service stuff at line rate. It's pretty neat. It's pretty gnarly code as well. It's open source. You can go and look at that. But to make it work well, it's not quite the same. I don't know. My belief is that in the wider web app sort of kind of realm, you generally just spin these things up. You don't really care where they are beyond, is there enough basic CPU or disk or whatever to kind of support my function. With network, with vRouters, you really do need to know about the actual hardware that it runs on to a certain extent. You get this sort of scaling and flexibility, but you need to know that the CPUs support the necessary virtualization to allow kind of hardware access, to allow them to get control of the NICs. You need also generally to actually pin CPUs to particular interfaces within the vRouter in order to get that line rate performance, because otherwise they get distracted, you no longer get the caching benefits, and you just can't hit that number. So you really need to be much more strategic about how you put things out. We're starting to get hardware pass-through as well, where you've maybe got a really fancy Broadcom switch that you can make use of, or a Broadcom NIC that can be controlled as well. But that's kind of, I think that's fairly on the edge of kind of happening. In switching, there's a thing called Open vSwitch that has OpenFlow support at the top end. It can control actual physical switches if you wanted to, but it can also control virtual switches, and you can scale that across multiple instances. I don't know as much about it. It didn't perform great, and then DVDK support came along, and now apparently it's great. So you've got that as well. And then the next big area is network functions virtualization. So when I refer to all those networking features that existed on the routers, and the idea is that instead of having that fully integrated into a vRouter or a vSwitch, you can break it out into a separate thing. So we already have this to some extent with firewalls. There's a company called Fortinet that make a firewall that you can run as a VM, and you can but you need to figure out how do I get my traffic to kind of run through it. And there's all kinds of other applications that are coming through this, like WAN accelerators, like VPN kind of usage. And the real trick is figuring out how do I deploy these things, and how do I get the traffic, how do I configure them such that the traffic is going to go through the various things. I mean, do we really want to go from a place where we had physical boxes that we kind of wired up together and that was fairly easy to do, to now we have to specifically deploy virtual instances of these things and figure out, well, how do I patch all these things together? You may be saving a bit, but logistically, you've kind of got the same management problem. And that's where the next thing kind of comes in. I will say that on the network function virtualization side of things, it's very poorly defined at the moment. It isn't like there is a standard for how you define or create a virtual network function, and then you can sell that to anyone that's got a device that supports it. It's a moving target in terms of standards, and it seems quite hard to consolidate for some reason. Orchestration solves that management problem, or is supposed to. It is kind of the holy grail of network management. The idea that you can have a single portal that you go to, and you can see your entire network, and you can configure all of the devices from a nice little web GUI. It is the panacea that we have been promised for a long time. I don't think we're quite there yet, but there are many things that are maybe moving towards it. The Linux Foundation has been quite a big supporter of many of these projects. And a lot of them are really conglomerations of other things. There are lots of other little things that have been packaged together as a lump and then turned into a named project. So for example, the PNDA is the platform for network data analytics. It is basically an ELK stack with some other network-related gubbins. ELK is Elasticsearch, Logstash, and Kibana, which you might have seen in other realms. And a lot of these things are kind of similarly bits and pieces that have kind of been bolted together in some way. There's actually a proliferation of these things, and the Linux Foundation is trying to have announced that they want to collapse it down in a more reasonable set of things, but, well, I'll believe it when I see it. Open Daylight is basically a switch controller. They claim it can control any device, and in theory you can configure routers with it through netconf or other, if you've got the right plugin, maybe other things as well. But really, the neatest applications of it are with switches, and you can have an application that embeds within it. It's basically a big lump of enterprise Java that can see, oh, all these switches are coming online. I'm going to display how it looks. I'm going to maybe have an OpenFlow controller in there and dynamically sort of configure them, etc. For routing, you can see what the configuration of things is. I think you can just about maybe change it, but we tried this, and it's fair to say that it wasn't fun. So we do have netconf is the big standard for configuring routers at the moment, which is still kind of gaining ground. And there's a thing called TLF, which is owned by Cisco, that can be used to configure these things instead. But again, it's fairly static and not very clever, or not the kind of AI intelligence that you might expect. The other big thing here, this massive set of letters, ETSI-MANO, is the European Telecommunications Standards Institute Management and Orchestration Platform. This is what it looks like. So this is a very traditional approach to designing a solution for things, where they've kind of got a bunch of clever people to sit down and design a very complicated picture, and there's a multi-point, many page standard for how these things are supposed to work. But it turns out that because all of these things are virtual and could be different things and have different support, is that there's actually very little specificity to it. You would kind of think that these links that are labeled, that maybe there would be a known protocol to run across these things, and that's not really the case. There's a suggestion for what it could be. The reality is nothing I'm aware of actually implements all of this. Things sort of map to some of these things. For example, the ONAP project is kind of the OSS, BSS side of things, and maybe the orchestrator. And then other projects are maybe focused on the VNF manager side of things, but it's all it's well intended, and it's an interesting idea, but it doesn't really match reality very well. So ETSI-MANO is this kind of standard for how we're supposed to develop orchestration software. There are various projects that are kind of getting in that direction. None of them have come to fruition yet. ONAP is the closest thing. It's the Open Network, write it down, Open Network Automation Platform. It is the merging of a thing called eComp with OpenO, Open Orchestrator. eComp, it's mostly eComp. eComp came out of AT&T. They actually use it internally for deploying their virtual routers and switches. And so it's supposedly battle hardened, and it has a great policy engine and stuff like that. We'll see what comes of it. It's something like 1 million lines of code that were just sort of dumped into the public at one point. It's hard really to know what to make of it or exactly where it'll go. I think there's a lot of consolidation to happen. But maybe what we'll get out of it is the grand unified UI that you'll be able to go in and you'll see all your devices and configure them all and be able to get metrics, and it'll sing and it'll dance, and you'll get a unicorn and everybody will be happy. Maybe. We'll see. Okay, so let's go past that guy. Right, okay. I've given a very high-level summary of a lot of stuff. Hopefully I've impressed upon you that networking is quite complicated, that there's a lot of stuff going on at the moment, and we don't really know where we're going yet. There's a lot of ideas. A lot of things are kind of touted as panaceas or saviors of networking, but not many clear winners yet. It's very much up for grabs, which is kind of what makes it quite an interesting field to work in at the moment. And with that, I will open up for questions. I realize folk might have had questions, I just simply weren't looking for them, so sorry about that. Right, okay.
It's Nick from Comms over here. So you've got these three kind of distinct trains, if you were.
Yep.
Do you have a feel for what you think will win out in the end, or is there kind of maybe some overlap between some of them? So I know that
Yeah.
quite a lot of disaggregation is coupled with orchestration at the same time, and again with virtualization and orchestration. So we've seen kind of orchestration now encompassing two of the other trains. So do you think
I think they're all right.
ultimately it'll be orchestration?
I think they are distinct concepts, but they sort of build on each other. And that's possibly why we're in such a mess. Is that there isn't like a clear next thing. There's various different things that really all need to be in place. Until you've got a base level with each of them, you don't necessarily have a fully working magic solution. So yeah, as you can see, the orchestration stuff, there's virtualization all over the place. And then the reality is that in some cases this will be, so your virtualization might be the operating system, the piece of software, and the hardware is the white box sort of hardware layer. It's in, or it might be a vendor thing instead. It kind of just depends. Yeah, it's kind of like they're complementary, independent things that will hopefully all come together to produce a magical new infrastructure for networking. Oh, good. Making them stand up.
So if I'm to understand properly, in the past there used to be like normal general purpose hardware did not do the job properly, and you had to make specialized hardware and a specialized software specifically for the purpose. And now, is the hardware that the virtualization layer, for example, will be running on supposed to be specialized as well for that virtualization? Or is it just general purpose hardware again? Because it's as if we skipped the step from going back to general purpose hardware and instead completely to like software solutions, and that sounds even less optimized than the specialized hardware that used to be there before.
It's a bit of that. The idea is that instead of having to get racks of Cisco kit that is all tied together, or HP kit, or whatever, and having to deal with their interface and their whatever they provide you and their rate of whatever service you're going to get. Instead, you can have racks of PCs that you get to decide who you buy them from. You'll have a range of vendors that you can choose the hardware optimizations from, and that you'll have software that ideally can work in your environment. There will be a degree of integration in the same way that if you look at what happened with Dell and the like, they had known good hardware. They kind of figured out this works with this, works with this, and this will all work reasonably well. They did a small amount of work to make sure it would all integrate nicely, and then they can sell a product as a lump. And that's kind of what we're missing, are these integrators that can figure out this is the hardware from this vendor, and this is the software that will all work together, and here's one that is nicely optimized for you, but we can also take this bits and pieces from different vendors and reconfigure it in a way that works better for you. Or even as a single customer, or if you're doing it yourself, you'll be able to sort of mix and match and sort of vary as time goes along. So yes, we had dedicated hardware, and now we moved to a point where the software could run anywhere, but the reality is to make it work really well, you kind of need to have partially dedicated hardware, or hardware that still works very well, but it could be on it. You can in theory run it on. You could have a whole bunch of these things and move your router to any of them, and it will kind of just work, kind of. I don't know if that clears things up.
So the title of your talk was sort of the future of networking, and it sounds like you're saying the future of networking is virtualization. What I'm maybe that's an oversimplification. I'm trying to understand what problem we're trying to solve here, because it seems to me like, we already have, well designed, standardized, and implemented virtualization solutions at layer 4 and above. So OpenStack, VMware. If you go up a layer,
you said OpenStack.
Sure, I'm sure that's a hot topic, but I'm just trying to understand, why is this a networking problem and not a problem at the layer above?
It's kind of, yeah, well, partly it's incumbent vendors and the like. Partly it's also this peculiar scaling aspect of the fact that with networking, you really do care how fast these things work, right? You have this constant stream of traffic, and you want to drop as little of it as possible if you can. And that puts pressure to really optimize and to specialize in a way that you don't really see in the application level as much. If you build a web app, usually you don't worry so much about optimizing the actual code stack to a certain extent. As long as you're not using a ridiculous algorithm, you can have a massive stack of Java. You can have pages and pages of JavaScript or whatever it is you guys do. And you don't care really too much how badly it performs, because the network is always your bottleneck, right? The time it takes for this data to get to your server and back usually should vastly outweigh what your actual application stack is worrying about. So normally the pressure is off to a certain extent. There are some applications where it's very much time critical, but most web apps, that's usually the case. And so you can virtualize these things quite well, and it doesn't really matter if it's not 100% efficient. If you get 50% efficiency from moving from a dedicated piece of hardware to virtualization, it's usually good enough. Also, you can make use of cloud platforms in a way that we can't rule quite with networking yet, because you don't care where necessarily beyond a general region these things are. You can accept the fact that you don't have much knowledge of the hardware it's actually going to run on, because again, all you really need is compute and storage and the like, and usually on the application side of things, that's good enough for you. Whereas with networking, you need to know, can I actually, what interfaces am I connected to, how are they connected, can I actually get control over these things so that I can make them run really effectively? And cloud providers are, to a certain extent, resistant to giving that control because they haven't had to do it for applications. It is happening to a certain extent. I think Azure's doing a reasonable job of trying to make this stuff more accessible for kind of networking providers and the like. But the likes of Google, on the other hand, they are trying to lock that down as much as possible. They just want to be seen as a compute blob that you kind of send stuff to, and aren't really that interested in allowing this kind of thing to kind of work effectively within their cloud. Does that answer your question?
I guess I'm just trying to understand the problem that needs to be solved. Like, what's wrong with existing routers?
They're too expensive. They might.
Okay, so I wanted to just put in a bit of a historical context
Yep.
on this, because you were kind enough. You mentioned Spider.
I
used
did.
to work for Spider, and I just wanted to say that when I worked there, when I started working there, Cisco were our main competitor. We were bigger and better than them then. And what the difference between what happened with the Spider story and what happened with the Cisco story was money. It was nothing to do with tech.
Yep.
And so when you said that they did the first multi-protocol router, they may have done the first one in the US. We, in Scotland, did the first one in Europe. And Scotland, back when I worked at Spider, we were Europe's largest indigenous manufacturer of this kind of technology. We were really good at it. It's great that we're still doing it in Scotland.
Yep.
So that's one comment. We've been doing this a long time. We're good at it, both the hardware and the software. And the second thing is, it's not about the technology, it's about the money. They could raise money, we couldn't. That's why they ended up being the billion-dollar company, and we end up getting sold to a really crappy American company.
Yep. I'll echo that. I think my opinion is that Cisco's been so successful because they have been sales-led. And this is the kind of opposite of what happened with DEC. DEC was engineering-led, and they missed the transition to PCs because they were more interested in making neater mini computers that were more amazing. Whereas Cisco's sales team have been very good at spotting where the market is transitioning from one section to another, and they've been pretty brutal about moving resources from one area to another. And that's why I work for Brigade now. So yeah, they were at one point the most valuable company in the world during at the height of the bubble, and not for no reason. Also, on the topic of Scotland being good at networking, arguably we started it. Alexander Graham Bell was born in Edinburgh, so.
Hi. Hi. Does that come through?
It won't. It's just for the live stream.
Oh, it's for the world, right? Okay. What commercially viable white box switching and routing products are there currently available? Because I can buy a switch for like $1,000 or $2,000, and they're quite good now. You can get like 10 gigabit copper ports and stuff on them. So is there any available now you can buy for like, 500 quid or something that you can put your own software and all the rest of it on?
Good question. I know that Cumulus they've teamed up with somebody. It might be Supermicro, it might be somebody else, and they've kind of got a matched pairing of our software will run quite nicely on this. We've validated that that'll work. There aren't that many, but there are a few kind of folk dipping their toes in the water. Are meant to allow Cumulus Linux and stuff like that onto their switches. Yep. Yeah, so there you go. There's another option. It's kind of still early days and still experimental. And I think we're at a point where you could probably put something together yourself, but it might cost a fair bit. And exactly how useful it is kind of, it's not really at the consumer level yet, is the problem. But like I said, there are a couple of folk that are now giving offerings. They're testing the waters to see what is going to sell and the like. So it could well be this year and the next that you're going to see a big swing. Apparently, white box is now 20 to 25% of the switching and routing market. And the reason for that is because your massive companies like Amazon and Google and Facebook, if you factor in what they've built for themselves, that's how much of the market that is effectively been taken up already. It's just making it available to smaller enterprises. It seems to be taking a bit of time, and it's partly because the standards just aren't there yet, and we're kind of waiting for it all to shake out.
So a lot of this virtualization, basically, we're still on the sort of just using a quad card, OCT card, networking card. That sort of thing, really. That's where we're still at on this in terms of white box hardware you can buy.
Yeah, I mean, you could take a small factor PC, shove in one of these quad NIC cards, put Linux on top of it, install Quagga on top of that, or free-range routing now, and you've got a white box solution. And that's basically something akin to that is what AT&T did. For a short-scale trial. So we're at that kind of point where you can put something together. The problem is that Linux by itself is not particularly well optimized for network transmission. It's why we need things like the DBDK, which runs in user space, in order to kind of make more efficient use of the NICs. I think it's getting better, and I think there's a project to actually pull some of the DPDK style stuff into the kernel. I forget what it's called. So it might change in the future, but at the moment it's still, that's the problem a lot of folk have. If you've installed VIOS, which is what Viata used to be, then you are basically just using the Linux networking stack, and you'll find that you're not going to get 10 gig line rate out of any NIC that you put in there, even though it will be able to send traffic over it. The bottlenecks just appear pretty fast, and I realize I've taken longer than I expected. Any last questions?
Yeah, I was just wondering what your networking setup at home was.
You know what? It's really stupid. It is a BT Home Hub. if I'm lucky, I might get some prototype hardware to play with in the future, but it hasn't happened yet, and it might never happen, given that I don't know what's happening with my job. I do have colleagues that have that run the vRouter at home, and they report and they find bugs and file them and get them resolved. But it's not a general thing that we all do. I generally, networking is complicated and annoying. I had my fun with it in my uni days, and if I've got something that just works, that's kind of, I'm at that point where I do this for my job. I don't want to have to do it at home. So very good. All right. So I will be available later for chat and the like. So yeah.